So, ladies and gentlemen, we are all welcome to my YouTube channel. Today, we are going to look at the concept of chemical kinetics. And if this is the first time you are coming to my YouTube channel, please subscribe. So, what is chemical kinetics? So, from the word here, from the topic here, we have two words: chemical and kinetics. So whenever we say kinetics, it's actually come from the Latin kinesis, and kinesis means movement. It means movement. Then of course we have chemical. So the chemical here is just trying to indicate the reaction. The reaction. So when we say chemical reaction is when you have a reactant and the product. So whenever we say chemical reaction, the first thing that will come into our mind is reactant and product. So reactants, then to products. So when you say chemical reactions, it means that it's a process that leads to the combustion of the reactant to products. So that is chemical reaction. The chemical reaction is when you have reactants that combats the products, and that is chemical reactions. Like for example, we will give examples of the chemical reaction, like we have hydrogen plus oxygen produce water. So in a chemical reaction, the reacting particles or the ingredients that are used for the formation of the products are called reactants. And of course, what you produce at the end of the reactions is called products. So now we are going to look at the chemical kinetics. Chemical kinetics means the rates of the reaction. The chemical kinetics means rates of the reaction. And what is rates of the reaction? The rates means speeds of the reaction. The speed of the reaction. That is how long, how substances are converted, or how the reactant are converted to products with time. And that is the rate of the reaction. And of course, when we are saying reaction, in the process of the reaction, the reactant particles are the one that are reacting to form a product. So therefore, we expect the reactant molecules to be decreased and the product molecules to be increased. So therefore, in the chemical reactions, we have reactant and we have product. So is the reactant that are combating, or is the reactant that are changing to products. So therefore, in the rate of the chemical reactions, the reacting particles, their concentration or the concentration of the reacting particles is decreasing, while the concentration of the product is increasing, because, like for example, in this case, hydrogen and oxygen are combating to produce water. So it means that in this case, as the reaction proceeds, hydrogen and oxygen concentration will be decreased, while the concentration of water will be increased. So that is why when we are talking about the rate of the reaction, generally, the concentration of the reactant particles is usually decreased, while the concentration of the product is increasing. So that is why in many cases we use graph to show the progress of the reaction. The progress of the reaction, and this is time. We have time here, and we have concentration. We have concentration from our y-axis. So we have concentration. So it means that whenever there is a chemical reaction, we expect that the concentration of the reactant will be increasing with time. So this indicates the concentration of reactants. So it means that as the reaction is progressing, the concentration of the reactant will be decreasing, while the concentration of the products will be increasing. So that is usually happen in this case. So you see, it means that from here, the concentration of the product will be increasing, while at the same time, the concentration of the reactant will be decreasing. So in the rate of the chemical reactions, it's just trying to measure the appearance of the product, how the product is appearing, while the reactant is disappearing. So that is why when we say rates of the reaction, it means there is the combustion of the reactant to the product, or formation of the product from the reactant. So that is why if you want to show how this rate of the reaction lies, is simple. Maybe let's say we have something like this. So let's say now you have a reaction that is taking place. So this is the reactant here. These are our reactants. This is reactants, and this is the products. This is the products, and this is the intermediate states of the action. So it means that at this point, the reactants here, they are all red in color. They are all red in color inside the reactant system. So, and that is at time zero. At time zero, all the reactant particles are there, and the reaction did not start. But as the reaction starts at 45 seconds, the concentration of these reactants begin to disappear, while at the same time the concentration of the product is also appearing. So that is why at the intermediate state of the reaction, you will be able to observe that here we have our products that are black in color. So it means that at this intermediate state, some of the products have already started forming, and at the same time some of the reactants are started or have already started disappearing. So it means that at this intermediate stage, you still have some of the product being formed, and some of the reactant also start disappearing. So that is at the intermediate stage. But at 45 seconds, at 90 seconds, that is at the completion of the reaction. When the reaction is completed, it means that all the reactant particles will disappear. So that is why here there is no any rate material, or there is no any rate reactant molecules. So there is no rate molecules, because the rate molecules are the reactant molecules, and they are all disappear. And here we have black molecules, and these black molecules indicate that all the reactants are completely converted into products, and that is what we call rates of the reaction. So when you say the rate of the reaction, it means the disappearance of the reactant with time, and also appearance of the product with time. So that is why if we want to measure, and of course in chemistry we have different ways that we can monitor, or that we can assay the rate of the reaction. We have different ways that we can apply to assay the rate of the reaction. Maybe in the case of color formation or decolorization. So we can use, like for example, we can use calorimeter, color Colorimeter is an instrument in chemistry that we use to measure the color of a particular molecule. And of course, we also have spectrophotometry. So you can also use spectrophotometry to measure the appearance and the disappearance, the appearance of the product and disappearance of the reactant based on their conjugated structure, based on the conjugated structure nature of the molecules. And we can also use radiometry. Radiometry is also another method of measuring the rate of the reaction. You can also use, that when we said radiometry, it means that based on the radioactive nature of the reacting particles or of the product's molecules. And we can also use fluorimeter. So these are some of the methods. These are some of the methods that you can use to measure the rate of the reaction. So whatever method you use in measuring the rate of the reaction, so we have a way of actually measuring this rate of the reaction. So in measuring the rate of the reaction, we can, one, rate of the reaction can be measured based on appearance of product and disappearance of the reactant with time. Appearance of the product and disappearance, appearance of the products and disappearance of reactant with time. So therefore, the rate of reaction can be measured in terms whenever we have a bracket like this in chemistry. It means whenever we have this kind of bracket in chemistry, it means it's a concentration. So we can measure the rate of the reaction by change or by disappearance of reactant, disappearance of reactants. Disappearance of reactants by T, or it can be measured as the appearance of the products with time. So that is how we measure the rate of the reaction. So to measure the rate of the reactions, you can measure its rate of reaction by appearance of reactant with time, or disappearance of reactant, or appearance of product with time. Let me now just let us now take example. Assuming now we have a reaction like this. Let's say we have H2O, H2 plus oxygen, then we now have H2O. So this is a reaction, but of course we have to balance the equation. Here we have hydrogen, we have 2 hydrogen, and here we have 2 hydrogen. But we have 2 oxygen here and we have 1 oxygen here. So therefore, if we can add 2 here, it means that we have 2 times 2, we have 4 hydrogen and we have 2 oxygen. So therefore, we can also add 2 here, making it 2 times 2, 4. So it means that we have 4 hydrogen and we have 2 oxygen. So the equation is now balanced. So how are we now going to measure the rates of this reaction? So to measure the rate of this reaction is simple. We are now going to take the rates of the reaction, the rate of the reaction can be measured in two ways. Either by measuring the disappearance of this reactant or appearance of the product with time. So therefore, you can now see the change in concentration of hydrogen divided by, of course, we have 2 here. So it means that we have 1 over 2. So we have that T. So we have 1 over 2. We have 1 over 2 because we have this 2. So it means that, but here it must be negative. So we are going to have negative. Why is it that it is negative? Because the concentration of the reactant is decreasing, is not increasing. Once the reaction started, it means that the concentration of the products will be increasing while the concentration of the reactant will be decreasing. So that is why if you are measuring the disappearance of the reactant, it always comes with negative. And of course, the coefficient of the element usually comes as a denominator. So therefore, we have minus delta change in hydrogen concentration by 2 delta T, or minus change in concentration of oxygen divided by delta T. So you see, if you can now see this, all this and this is just that you can measure the rate of the reaction by just measuring the disappearance of hydrogen gas, or by just measuring the disappearance of oxygen. And of course, at the same time, you can also measure the rate of the reaction based on the appearance of the product. And how are we going to measure the rate of the reaction based on appearance of the products? It's now, like for example, this is water. So to measure the rate of the reaction using the products, what we are going to do is, we are now going to say the rate of reaction, is equal to, so here, because it's product, so we are talking about appearance, so it's going to be positive. So it's positive, therefore we have now change in concentration of water molecule divided by 1 over 2, then delta T. So it means that when you want to measure the rate of the reaction, you can measure the rate of the reaction by measuring the appearance of the product, which is always positive, or the appearance of the reactant, which is always negative. Because the reactants are decreasing while the products are increasing. So this is how to measure the rates of the reaction. So let's now look at another example. So we have an example here. What is the rate of disappearance of ozone, or how is the rate of disappearance of ozone related to appearance of oxygen in the following reaction? So we have 2 molecules of ozone gas. We have 2 molecules of ozone gas here. We have 2 molecules of ozone gas. So it decomposes, it will give 3 molecules of oxygen. So the question is just trying to show how is the rate of disappearance of ozone is related to the appearance of oxygen. So I think this is simple. So since this is an oxygen, so to measure the rate of the disappearance of oxygen here, to measure the rate here, we are now going to see the concentration of the disappearance, or the concentration of the disappearance of oxygen with time. So therefore, we are now going to have, since it is disappearance, so this is our reactant, so we have minus. We are going to have minus. So it's going to be, so we have minus. So this is the oxygen. So we are now going to set, since here we have 2 molecules, we are going to set minus 1 minus 1 all over 2, and we have change in ozone concentration with time. So it's going to be negative. So this is the disappearance of the ozone, and then we are now going to look at it from the point of appearance of oxygen. So because here we have oxygen, so here we have ozone, and here we have oxygen. So we are going to measure the rate of the disappearance of ozone, and number of molecules here in ozone is 2. So that is why we have minus 1 over 2. Then we now have change in the disappearance of oxygen with time. So after this, then we are now going to get that of oxygen. So therefore, since oxygen is the product, so it's going to be positive. So and the number of molecules of oxygen is 3. So we have 1 all over 3. And we now have change in oxygen concentration divided by delta T. And the first component here, it means from here to here, it just shows the relationship, or show how ozone and oxygen related in terms of appearance and disappearance. So now, then after showing the relationship, and then the next thing, if the rate of appearance of oxygen is given as 6.03 times 10 raised to the power of minus 5 molar second. And I forget to tell you that the USA unit for the rate of the reaction is molar as. And of course, here, the rate of the appearance of oxygen is given as 6.02 times 10 raised to the power of 3 at a particular instant. So at power minus 5 instance. So now what is the value of the rate of disappearance of ozone? So it's simple. We are now going to measure it. And how are we going to measure it? We relate it with this. Since it is already given that the concentration of the oxygen, or the rate of the appearance of oxygen is 6.02, so we are now going to use it and relate it with this equation to find that. Okay? So that's the top second components. Then we are now going to say for the ozone, we have 1 over 3, then times concentration of ozone divided by, sorry, for the ozone is 1 over 2, because it is 2 here. So it's 1 over 2, then with time, then we now have that of the ozone, sorry, that of the oxygen, we have 1 all over 3, and of course we have the appearance of oxygen, then divided by delta T. So for the oxygen is given, so we now have 1 all over 2 times ozone, concentration of ozone, divided by T. So, and of course we have 1 all over 3 here times, and the rate of oxygen is already given, which is 6.01 times 10 raised to the power of minus 5. So therefore we are now going to cross multiply this. So at the end we are now going to have oxygen divided by delta T. Then we now have, because so 2 times 1 here, we have 2 divided by 3 times open bracket 6.02 times 10 to the power of minus 5. So after we do all our calculation, so the concentration of ozone here, or the rates for oxygen is now, sorry, we want to get the rate of ozone. So therefore from this you see that we have that of ozone and we have that of oxygen, and the rate of oxygen is already given as 6.02, and that of ozone is not known. And here we have 1 over 2. So we have to cross multiply. Then after we cross multiply, we are now going to have the rate of ozone is equal to 2 all over 3. And after we multiply this, we are now going to have 4.0 times 10 raised to the power of minus 5 molar per second. Molar per second. Molar per second. So this is one of the examples of how to calculate rates from a given questions. Like for example, here in this questions, the rate of oxygen is given, which is the product, and the rate of ozone, which is the reactant, is not known. So you have to relate them. And after you relate them, then you calculate for the unknown using the known rates. Okay. So now the next thing that we are going to look at is how or what are the factors that affect the rates of the reaction. So now we are going to look at the factors affecting rates of the reaction. So generally we have some factors that may increase or decrease the speed of the reaction. So we are now going to look at them one after the other. So we are starting with temperature. Temperature is one of the first factors that affects the rate of the reaction. For one, we have temperature. So you have temperature. So generally, if you have a reaction, let's say you have A plus B, you get C plus D. So whenever you increase the temperature of the reactant particles, the increase in temperature generally increases the kinetic energy of the molecules. It increases kinetic energy of the reacting molecules. So generally, if you increase the temperature of a particular reaction, it increases the kinetic energy of the reacting molecules, which is the reactant. So it increases their kinetic energy. It means that their movement will increase. And once their movement is increased, it means that there is a chances that these reacting molecules will be collide, and the collision is generally elastic. It's generally perfectly elastic. So it means that the more these reacting particles collide with one another, the more they collide, the more they provide, or the more they get sufficient energy that will make them to easily collide head to head for the reaction to take place. And of course, it's this energy that allows these reacting particles, after an increase in the temperature, that allow the reacting particles to jump the activation energy. So generally, an increase in temperature of the reaction, an increase in temperature of the reacting particles generally increase the rate of the reaction. And if you decrease the temperature, then the rate or the speed of the reaction will decrease. And how is this increase in temperature affect the rate of the reaction? Is by increasing the kinetic energy of the reacting particles. And once the kinetic energy of the reacting particles is increased, then the collision between the particles will increase. And as a result of that, they will get sufficient energy that will make them to easily jump the activation energy for the reaction to take place. So generally, temperature is one of the factors that increase the rate of the reaction. So as you increase the temperature, then the rate of the reaction increases. So therefore, increase in temperature leads to increase in rates of the reaction. So it means that it is a direct relationship. Well, the first one, and second is concentration of the reactant. Concentration of the reactants. So generally, if you increase the concentration of the reactants, like for example in this case, you have A and B. So as you increase the concentration of A, then the reaction, or the rate of the reaction will increase towards product formation. So it means that if you increase the concentration of either A or B here, or both A and B, it means that the speed of the reaction will increase. So therefore, the concentration of the reactants is also affecting rate of the reaction. So the more you increase the concentration of the reactant, the more the speed of the reaction. So generally, concentration of the reactant reacting molecules or increase in the concentration of the reactant generally increase the rate of the reaction. So that is the first one, and then the third one, that is the second one. So the third one here, we have catalysts. We have catalysts. What are catalysts? Catalysts are molecules that usually speed the rate of the reaction. There are molecules that speed the rate of the reaction. There are some reactions that they can take years, there are some reactions that they can take months, but as a result of the presence of the catalyst, the reaction will be the catalyst will increase the speed of the reaction. And how is this catalyst generally speed the rate of the reaction? Like for example here, if we have the reaction profile diagram, let's say this is our reaction profile diagram, and we have something like this. Let's say we have something like this, and this is our reactant. So we have A and B here, and this is our product where we have C plus D. And of course, from here to here, we have our EA, that is activation energy. So the presence of the catalysts generally decrease the activation energy. And what is activation energy? Activation energy is the energy barrier that must be overcome before the reaction takes place. So it's an energy barrier that generally the reacting molecules must cross it. They must cross it. So it's a barrier between the reactant and the product. So it means that the reactant particles must overcome this activation energy before the reaction takes place. So therefore, the presence of the catalyst, what catalyst does is usually decrease the activation energy. And of course, once the energy is decreased, it means that the rate of the reaction will increase. So that is what happens. So catalysts reduce the activation energy, and once the activation energy is reduced, then the reaction will proceed. So that is in the case of catalysts, and of course, we have a typical example of catalysts is enzymes that usually act in living system. So enzymes are organic catalysts that speed the rate of reaction by decreasing the activation energy. So that is what enzymes did during the course of the reaction if you add them. And one thing with these enzymes, they are not consumed, they are not used up during the course of the reaction. So if you have enzymes convert A to B, it convert A to B, so that enzymes will not be part of B. It means that it will be recycled and used for another round to convert another A into another. So it's not used up and it's not consumed during the course of the reaction. So that is for the catalyst. So these are the three factors that affect the rate of the reaction, and we have fourth one. So the fourth one, apart from temperature, concentration, catalyst, then the fourth one we have surface area. We have surface area. So generally, an increase in surface area also increases the rate of the reaction. How do you increase the surface area of the active molecules? So you increase, if you have something like this, it's big, and if you now round it into smaller particles like this, it means that from here to here you increase surface area. So generally, an increase in surface area also increases the rate of the reaction. So if you decrease the surface area, then the rate of the reaction will also decrease. So that is that is in the case of surface area. So increase in surface area also leads to increase in the rate of the reaction, and decrease in surface area leads to decrease in rate of the reaction. And then the fifth one is pressure. So generally also pressure is only applied to a gaseous reactant, and It only apply to the reaction that involve gaseous molecules. So, and generally, increase in pressure also lead to increase in the rate of the reaction. So, ladies and gentlemen, thank you for listening, and we will meet in the next video where we are going to talk about rates of the reaction. And if you did not subscribe, please subscribe. Thank you.